Um, Now we are talking about the image formation in the process is called the refraction. So we will see that image will be formed when two refracted ray refracted rays two refracted rays appear to meet, okay, or intersect. So this is the condition for two image formation, okay, image formation. So let's see here, in this case of a stick, I'm drawing the similar picture over here. Okay, this is the upper medium is air and the medium down is water. So let's talk about the point P of the stick. Okay, so say, for example, if I have the point P here, I'm drawing the perpendicular line. This is the outward drawn perpendicular. Okay, so this is the P, this P is any point on the stick. Okay, so you know that to get the image, we must need two rays. So I'm taking one ray, just like this. So light is traveling from water to air, so it will bend like this. Okay, this is my one, this is one prime. If I produce back, this refracted ray will come up here. I will consider the other ray, say for example, I'm considering that a 2 prime. Okay, I can take any one, say this one. This is my 2. Okay, this is my first incident ray, this is my second incident ray. If it go to the air, it will bend like this. This is 2 prime. These two refracted ray will meet at a point. Okay, so this means in this case here, 1 and 2 are incident rays, and 1 prime and 2 prime are refracted rays. You see here that two refracted rays not actually intersect. Okay, but it appears to meet. Okay, it appears to meet. So in this picture, it appears to meet, say in this picture, it appears to meet at Q. So point P appears at Q. So this means Q is the image of P. So that means, that gives the idea that P appears at Q. Okay, P appears the point at Q. That's the reason the stick appears to be bent when it is kept underwater. So only the portion which is underwater appears to bend. Okay, so let's talk about, in this case, real depth and apparent depth. The same scenario just we are doing here. So this is the exactly same picture. So this is the, say, this is the actual location of the object. So we can say P is the object as before. Okay, and Q is the virtual image. Means if you put a coin at P, it appears at Q. Okay, so this means, say in this case, if you measure the distance from O, so OQ equals HI is called the image distance or the apparent depth. Image distance. Okay, we can also call it the apparent depth. Means if we put a coin at point P, it appears at Q. Okay, so, and you see OP is S naught, we call it object distance. Object distance. We also call it the real depth. Real depth. So the key point here is this: the object at P appears at Q. Okay. So we can prove, or we can show, that this result. So H naught, okay, H naught over Hi, real depth by apparent depth, equals we can write like we can write at N2 eta 2 over eta 1. Okay, so what is eta 1 and eta 2? So in this scenario, we can say like we can say N2 over, just wait for a minute, I will check the equation. So here we can say this N1 is the refractive index of, say for example, in this case, say it is with respect to air. So refractive index of air, or the first medium, we can say this as a medium 1. Okay, and I will say this as a medium water as a medium 2. Medium 2. Okay, so N2 will be the refractive index of, in this case, it is water. Okay, so we can prove this result. Now let's come how we can find the relation between object distance, image distance, and the refractive index in the case of refraction. Okay. Okay, so let's see. In this case, P is the location of the object distance, object point. So this is the first medium. Say the medium in this side has a refractive index, this one, N1, and the medium in the spherical surface has the refractive index of N2. Okay, so this is the object position, and in this picture, this is the center of the sphere. We assume that this is a spherical part of the sphere. Okay, and this is the image point. So clearly, this distance d1 is, we call it di. Di is the object distance. Okay, and in this picture we have so this is, if we measure from this point, say this point is from this point O, so this distance is basically OP. Okay, and we'll see DO is the image distance. Okay, image distance, image distance. So this is OP prime. So be clearly that this image is due to reflection, due to reflection. Okay. If we use this, and R is the radius of and C is the center of this spherical surface. Okay, this is the spherical surface. That's why this R is the radius. This R will indicate you the radius. So based on that, if we do some math, based on that, we can prove that finally we can write this in the form of equation as N1 over, let's write so down. So we can prove that N1 over D naught, okay, or we can use the symbol, say D naught, okay, plus N2 over Di equals N2 minus N1 over R. Okay, so we can show this result. So here N1 and N2 are the refractive index. R is the so R is the radius. Okay, so we can locate. Yeah, we can use this equation to find the position of image. Okay, so for example, say for example, if we have a plane refracting surface. So for example, this is just a case. I will write like a box. If for plane refracting surface. What do you mean by plane refracting surface? Means we are talking about this side is plane, state like this. So this side may be, say for example, air, one medium, other side we have medium water, this side is plane instead of curve. If this is the scenario, this is the plane. If this is the case, then you know for the plane, R is having to be number is infinite. Okay, if we do that, if I plug in here, we'll find N1 over D naught E plus N2 over Di, okay, equal to 0. So this result that I showed here is same as we did before. This is a special scenario, just this is the equation we can use. Okay, this is very similar equation, we get it. Next, let's talk about the lens. Okay, in the lens, we follow the laws of refraction. So let's talk about different kind of lenses. So lenses are supposed to be a part of two spheres. Say I have one sphere here. I'm drawing one sphere here. Okay. It may have some center. So it may have center C1. It may have radius R1. Okay. I will also draw the other sphere. It has separate center. Okay. So may have this radius may be same or different. It is R2 center C2. Okay. So we have two spheres. So this is, you consider the two spheres with radius already R1 and R2. So if you just consider this part, this behaves as a lens. Okay, so this is the example of convex lens. Okay, we call it the convex lens. So in this case, we have to define the axis. So you know that lens has two surfaces. First surface 1 and second surface 2. It has two surfaces. It has two centers, one for one surface, one for the another surface. So this is C1, this is C2, okay? So if we join C1 and C2, this is called the principal axis. And the axis and this point where we're talking about, this is the center of the lens. This is called the optical center. This is called the optical center. Okay. Same case will apply for the case of the concave lens. Okay, let's see that. Say again, say we have two spheres again. We can take, like, say I have one sphere is this. It has center C1, and this radius is R1. I have the other sphere, center C2. This radius is R2. Okay. Then we can consider this part. Okay, like this. This will be considered as concave lens. So as before, if this is our concave lens and this is the axis, this is the principal axis which joins C1 and C2. Okay, C2, this we can consider different scenario. So this point center is called the optical center. Optical center. Okay, let's define the focus. How we define focus? Okay, so let's take with the convex lens. Okay, this is the axis. This is the principal axis. Okay, so be careful that this is the axis of the lens. This is the principal axis. So this is the optical center. So you know that any ray parallel to the principal axis after refraction will meet at a point. 1 and 2 are incident ray, and 1 prime and 2 prime are the emergent ray. Emergent ray in the sense that light travels from here, light travels from air, glass, again in air. So there is two, here refraction happens 2 times. So refraction 2 times. Okay, so remember 2 times. At first, air to glass, and then glass to air. Glass to air. Okay, so in this scenario, this point is called the focus. Okay, but be careful. One should be careful that it is the O is the optical center. So O is the optical center and F is the focus. Okay. So in this picture, OF is equal to small f is the focal length. So I want to warn that this f is not equal to, for example, r/2 for the case of mirror. So not true. This is not true. Depending on the condition, if we take the exact value, then it may not be true for lens. Okay, but this is true for the mirror. We can also incident light from the other side. See, this is the convex lens. If we hit the light parallel to the principal axis, after refraction at two surface, it will meet to that side. So we can say f prime, but this distance is exactly same. So what I'm saying is that OF is exactly equal to OF prime is equal to F. So lens has two focus. So lens has two focus. So we call it foci. Okay. So this case, the image, the focus point is real. This focus point is real because it happens because of the actual intersection of the rays. Let's talk about the other, say, let's talk about the focus for concave lens. Okay, so let's draw the picture. We have for the concave lens, we have this kind of image. This is the axis of the lens. This is the principal axis. Okay, so when we hit the light parallel to the principal axis, after refraction at two faces, this one will bend like this, 1 prime. 2 will bend as 2 prime. Okay, so when you produce back, it appears to meet from this point. So this is called the focus. So this focus is virtual. So as before, the concave lens has two focus. As before, one focus to one side, other focus to the other side, but this length and this length is exactly equal length. From, we can say F and F prime, if we measure from O, so OF and OF prime, which is equal to focal length, will be exactly same. Okay. So let's see about object distance, image distance, and focal length in a lens. Okay, so just take one example of the convex lens. So this is the convex lens. Okay, so this is the principal axis. This is the optical center O. Okay, so O is the optical center. Okay, so you know that in the case of lens, we have two focus. One is EF to this side, other is EF. Instead of R, we call it R, and we don't use R here. So basically, we call it twice F. Okay, so other position will be also twice F. So this means OF is focal length. Focal length. Okay, so twice F is at a distance twice of the focal length. Okay, say I put one object somewhere, say for example here between F and 2F. This is my object, real object. So I say this is my height of object is a height of object. Say for example, I would say for example, I would say H naught. So to the diagram, ray diagram, I will take one ray parallel to the principal axis. Okay, according to the definition of focus, it must pass through focus. Here is a refraction. Okay. Other ray through the optical center must pass through a state without bending. Okay. So you see two refracted rays. Okay, this is the one ray, this is the second. For that one, refraction is 2, up to is 1 prime, and this is 2 prime. They intersect at this position. So hi is the height of image. This is your image. Okay, so this image you can see here is the real, because it is formed by the actual intersection of the refracted rays. So for example, here you can see here, h naught is the height of object, and I is the height of image. Height of image. Okay. So from this picture, we can clearly see, say this distance d naught is the object distance, and this distance di is the image distance. Okay. So d naught is the object distance, and di is the image distance. Okay. If this is the case, we can prove, we can show that the result 1 over d naught plus 1 over di equals 1 over focal length. Okay, this result is true for both lenses, either concave lens or convex lens. So this is true for both, convex and concave lens. Okay, so in this scenario, we are assuming the convention, sign convention is the important part. Sign convention. That means what sign convention will use? Okay, so in this case, we are assuming di is positive for real object, and d naught is positive for real object, and di is also, we take positive if it is real, but we take di value negative if it is virtual. Okay, and focal length is positive for convex lens and negative for concave lens. Okay, so you have to stick one sign convention throughout the topic or problem. Okay, so this is the concept behind the object distance, image distance, and focal length. Okay, let's see how object distance, image distance relate with the focal length. Okay, so focal length will be the same. Object distance could change, image distance could change, the focal length will remains the same. So for example, as before, I will show you the simulation. Okay, say now clearly in this simulation, you see that focus, for example, in this case, let me write focus. We wrote here, it's basically 4. Okay, So your twice f is basically 8. So if this object is beyond twice f, okay, this real object is yet beyond twice f. So for the case of convex lens, if you put any object beyond twice, image will be formed. This image, you see, this is the intersection of actual refracted rays. So this is the real image. It is formed, you see, it formed, you see here, it is formed formed between f and 2f. So your f is here, your twice f is here. So it is f position, this is the twice f position. So image, this image formed in between somewhere, or formed in between means somewhere f and twice f on other another side of the lens, another side of object from lens. Okay, so this means object and image are not in the same side. So you can clearly see that size is smaller. The height of object is basically 2. If you look at here, height of image is 1 point. If you just take the positive value, height of image will be just 1.57. Okay, it may be meter, centimeter, whatever. So size will be smaller. So if you change the position, the object distance could change, image distance could change, but the focal length will be the same. Okay, we can try the other options. Okay, let's move this at this position at 2f. You see, if you put an object at 2f, now the object is situated at 2f position because your focus is basically 4. Okay, your twice f is basically 8. So if you put object at twice f, image will be also formed at twice f. So image is also at twice f. You can see they are of same size. So we need to adjust that a little bit. So it's of same size as object. Okay, let's try the another options. Let's try the another options. Say now the object is in between focus. This is the scenario. Now see, in this scenario, your focus is here, object in between. So your object in between focus and the optical center. Okay, if this is the case, now virtual image, you see the image is not real. You see these two refracted rays will not intersect anywhere. So you get the virtual image. Okay, so image will be virtual, upright. The height of image will be higher, bigger image. You can see here, image size is bigger than the height of the object. Okay. Now let's talk about position and nature of image formed by the concave lens. So I will take you again to the simulation. Now in this time, you see our lens we used here is the concave lens. Okay. If I put object anywhere, This is a real object. Okay, this is a real object. Then if you see this picture diagram, image will be virtual. Okay, so virtual image will be formed, and size, if you compare that, height of image will be smaller. So this is virtual and smaller in size will be formed, and it will be upright. Okay, so that's how why using that equation we can predict where the image will be formed in the case of concave or the convex lens. So the key equation we'll use to predict object distance and image distance is 1 over d naught plus 1 over di equals 1 over f. So in this scenario, and this object, this is your d naught, and this is your di, and this is your focal length, and this focal length, focus is here. So you can say our focus from this point. So this is our focus. So this equation can be used to predict position of image, and that value exactly matches with the simulated result. Okay. So this lens maker formula basically gives the relation between two radius of curvatures, relation between R1, what is the relation between R2, and it gives the relation between refractive index, eta 1 and eta 2, and focal length. So this gives the relation. Okay, this gives the relation between these quantities. So in this case, we have this lens. Lens has a refractive index eta 2, and we have other side, it may be air. So air has a refractive index eta 1. Okay, so this is the position of object. Okay, and this is the position of image. Okay, so you know that for that case, d naught is the object distance, and here di is the image distance. Okay, and if this is the scenario, we have a result. We can prove that. We can use this link to look at that. So it will be 1 over f equals eta 2 over eta 1 minus 1 over R1 minus 1 over R2. This result is called the lens maker formula. Lens maker formula means if you know those quantities, we can find the focal length of the lens. So you know that how we can consider which R1 is positive or negative. So in this case, we consider R is positive. Okay, R is positive for a surface. Convex towards the object. And R is minus, negative for a surface. Convex, concave towards the object. I use this convention, but you can use the other convention. Okay, this is called the lens maker formula. We can prove this. Okay, next part I'm talking here is that how we can draw rays if not parallel to the principal axis. So for example, this is just the general scenario. If we have this kind of lens, convex lens, if our rays are parallel to the principal axis, it meet at focus. Okay, but the same case, just look at that. If rays passing here is not parallel to the principal axis, but is still parallel, then they will meet in the focal plane. We call it exactly at the same location. They will not meet it here. They will meet at some point in the, this is called the focal plane. This is called the focal plane. So they will meet somewhere here. So this is also called the secondary focus kind of thing. Okay. So if you understand up to this point, you can practice this question by using the equations you have already known. Okay.